Bismillahirrahmanirrahim. Today we'll talk about non-regular language. We already discussed about the regular language. We already discussed about clean theorem as well. Today we will see how we can find out either a language is a regular or non-regular. By using a finite automata and regular expression, we have already defined many languages, and as per the clean theorem, if a language is defined by a regular expression, it can be converted into finite automata, or if a language is defined by a finite automata, it can be converted into the regular expression, transition graph, and so on. Although these languages have many structure, we have seen in the previous example that we defined the language with a required substring. We might have two A's. We might have either one A, or we might have, for example, we might have a language that consists of two A's, maybe in the start, that might consist of two A's, might be in the middle, or one A, so on. And we already discussed about the language that forbid some substring. For example, we discuss about the language that does not contain two A's together, or that does not contain maybe two B's together. And also we discuss about the language that either begin or end with some substring, maybe starting with A, ending with B, starting with B, ending with A, and so on. And the language with a certain even or odd properties, consisting of even number of A's or odd number of A's, and so on. Now we will see some advanced examples. We will turn our attention to some new types of language in order to find out either it's a palindrome or not, okay, or the language of all the prime words with the A power p is a prime number. We shall see that neither of these languages are basically the regular language. We can describe such type of languages, the one that is related with a palindrome and the one that is related with a prime number. We can describe those languages in the descriptive form in the English, but we cannot define or make the finite automata for that, because finite automata have a limited capability. That's why finite automata is not be able in order to define those language. So that's why what we need some more powerful machines. For example, let's see these examples. These are the example of the regular language with A star B or B star C, and so on. However, these are the example of non-regular language, which is A power n, B power n. We have done the example of A steric, B steric, but it is not mandatory that the occurrence of A will be equal to the occurrence of B. So this is basically a regular language. However, this one is basically a non-regular language, because here there is a restriction that the occurrence of A and the occurrence of B should be equal. Similarly, if you have a word V, and when you reverse the word, so this basically represent what? This basically represent the palindrome. So these are the example of the non-regular languages. Now, a language that cannot be defined by a regular expression is known as a non-regular language. And if something is not defined by a regular expression, so it is not possible to make the finite automata as well. By the clean theorem, a non-regular language can also not be accepted by a finite automata, or it cannot be accepted by a transition graph. All languages are it can be either regular, it can be either non-regular, or maybe none are both. Some languages you can consider it as, because all those machines that can define a non-regular language, for sure it can define a regular language. Now the question is how we can prove that, or how we can find out that a language is regular or not. As per the clean theorem, we know that whatever language, if a language is irregular, for sure it can be defined by the finite automata, and it can be defined by the regular expression. So if we are going this way to find out, either we can make a finite automata, DFA or NFA, or regular expression. So in this case, it will be really hard, So that's why it is written that proves that there is no DFA, no NFA, or a regular expression that accept this language. So it means that language will not be a regular. But the problem is, this is not an easy task. Why it is not an easy task? because we already discussed that sometimes, yani for a same problem or a same language, there are so many, ways in order to write the regular expression or to write the finite automata. So since there is an infinite number of them, so the solution is what we need. We need a systematic way. We need some sort of algorithm in order to find out that a language is irregular or not. And so far we have a solution which is known as pumping lemma. So we will see today what is pumping lemma, how we can come up with the idea of a pumping lemma. Let's consider first example. We have this here an example. Okay, here is a language which consists of a string. The string can be either empty, one time A, one time B, two times A, two times B, three times A, three times B, and so on. Keep in mind, we cannot say that this particular, string represent a language, and that language is basically, we cannot say that it is representing a steric B steric. Why it is not representing A steric, B steric? Because based on A steric, B steric, you might have only any B's with a zero occurrence of A's and two occurrence of B. However, this is not something that is acceptable by this particular language. Okay, so here you can see, for example, we have, these are the strings. So it represents a language which is A power n, B power n, where n might be equal to 0 because empty is allowed. It might be equal to 1, 2, and so on. Now, we can say, note that although L is a subset of many, regular languages, such that A star, B star, but in here, make sure that those, strings related with A star, B star, where the occurrences of A is equal to the occurrence of B. The language defined by AB. Also, in here, if you can see in this particular case, this A steric, B steric, it represent AB. Okay, khalas, this in yani is under this language. However, if it is 2 times A, 1 time B, no, this is not under A power n, B power n, and the language which, and the string which represent double B also come is something that does not come under A power n, B power n. Now, suppose that it is required to prove that this language is a non-regular language. How we can do this? We know that we can do it by using the pumping lemma. But what is the basis of the pumping lemma? Today we will see. For example, we know that L, for example, if we want to prove that it is a non-regular, let's prove it by contradiction. So we will assume that L is a regular language, and we know by the Kleene theorem that if anything is a regular language, it means it can be accepted by a finite automata. It means we can draw a finite automata. Since every finite, and we know that every finite automata should have a finite number of states. The language might be finite, the language might be infinite, but the finite automata must consist of, limited or finite number of states. Then the language being infinite will be accepted by F, must have the words, okay, of, for example, of the length more than. We will here only consider those words in order to, give the basis of the pumping lemma. So we will consider the length of those words that are more than the states, because we want to discuss some concepts which is a circuit. So that's why, in order to understand the concept of circuit, we need to consider those words that are more than the number of states, which shows that F must contain a circuit. Now, there are basically two things. One is basically a loop. Another concept is the circuit. What is a loop? For example, if you have a state, so loop is basically you started from the same state, you ended at the same state without, visiting any other state. However, in the case of circuit, what is circuit is, for example, I have this state, okay, I have here another state. So I moved from here to this one and then came back to this one. So this is basically a circuit that you started from one state and you reach to the same state, but visiting, some other states as well. So this is the circuit and this one is the loop. They are two different things. Suppose that, for example, we consider an example that it consists of 10 states, okay, and we have a string which is related with A power n, B power n, and here the value of n, let's assume, is 9. Okay, and you can see a power 9, b power 9, so altogether the string size is 18. 9 times a, 9 times b. Yani, okay, from the language L, and let the path be traced. So here we will trace the path. Let's assume this is the example. Okay, this is the finite automata. So here what you have, this is my initial state, this one is my final state. It is a power 9, b power 9. So what is the path will be, and 1 time a, 2 times a, 3, 4, 5, 6, 7, 8, 9. 9 times a, and 1 time b, 2 time 3, and then 4, 5, 6, 7, 8, 9. In this example, if you can see, here is basically what, here is one circuit, and here is also another circuit. Because why it is circuit? Because if I am at 9, okay, I can from here I can go from 9 to 10 and then 9. So there is another state involved, and here is also a circuit from 3 to 3, 4, 5, 6 to again 3. So here we have two circuit. This is circuit number 1. This one is our circuit number 2. Now, so what I did, we have a power 9 and b power 9. Now, what I did in a power 9, the occurrences of a, so look, 1, 2, okay? Inside the circuit, how many? 3, 4, 5, 6, 7, 8, 9. So one time circuit is repeated, okay? Now look, 10, 11, 12, 13. So it means every time when the circuit will be repeated, it is basically what? It is basically plus 4. Okay, so 9 plus 4 is equal to 13. So what we did, we came up with A13, B13. How we got A13, B13? Just, execute the circuit one more time. So the path A power 13, B power 9 still has 4 more A steps to take, which is one more time around the circuit, which was basically circuit number 1, and then followed by maybe 9 or more than 9 Bs. Assume that for example, let's assume this was our first assumption. We do another assumption for the same question, which is basically A power n, B power n. Let's assume we have 95 states, okay, and the circuit was 7 states long. We have an, if the input string is A power 96 and B power 96, okay, this string would produce a path through the machine that would walk up to the same circuit reading only because inside the circuit altogether your finite automata is 95 states. Inside that 95 state there was a circuit, and the circuit by itself is 7 state long. So it means that you have a circuit, that 7 states circuit, and inside the circuit only have only A's, okay, and began to a loop around exactly the same way. Yani how many times you will do, it will exactly the same. However, the path, so look, what we did previously, we were doing, 4. Why? Because we have 4 states involved in the circuit. Here we have 7 states involved in the circuit. So that's why A power 96 plus 7. So what we did, it is A power 96 plus 7. Okay, and B power 96 will be same. So 96 plus 7 is basically equal to 103. If you want, for one more time cycle, so 103 plus 7, which is equal to 1110. If you want to execute a cycle or a circuit one more time, so it will be 1110 plus 7. And if you want to execute one more time, it is 117. So it will be 117 plus 7 and so on. Okay. So however, you can see here, however, the path of A power 96 plus 7 B power 96 loops around the circuit one more time, then the path which is equal to A power 96 B power 96. So we can say that A power 1110 or A power 117 or 124 are also accepted by this particular machine. So if you want to generalize this thing, how we can generalize is that we will simply write, look, a power 96 and b power 96. And we know that every time it is equal to plus 7. So it is a power 7. And then here it will be m. Yani 7 you might have repeated 1 time, 2 times, 3 times, 4 times, and so on. So that's why we came up with this equation, a power 96, a power 7, then power m, and a power 96, where m is any integer, and it might be repeated 0 time, it might be repeated 1 time, it might be repeated any number of time. If m is equal to 0, it means it is a 96, b 96. If m is equal to 1, so it means that a power 96 plus 7 and b power 96. So it means it loop around the circuit one more time. Now consider this particular diagram. Now, but looping the circuit generated, this diagram is different than this one. Okay, here we have this 3, this 4, and here it is 6, and here it is 5. In the previous case, it was 5 here, it was 6 here. But the looping the circuit generated by the states, here it is states are yani 3, 4, 6, 5, and 3 again and again. This is the complete yani circuit with a edges once more, and f also accept the word because it is yani 4. So here what we did, 9 plus 4 and b power 9. So b a power 13, b power 9. If you can see, we can generate this, and our equation is a power n, b power n, where these ends are equal. However, here it is a power 13, b power 9. So in this case, 13 is not equal to 9. So it means that this particular word is not in the language. It may also be observed that because of the circuit we have discussed, F also accepts a language which is yani based on this particular equation. It says that a power 9. Okay, here it was 7, but because in the previous example the size of the circuit was equal to 7, but here in this case the size of the circuit is 4. So we write a power 9, a power 4, m, and b power 9, where m is equal to 1, 2, 3, and so on. If m is equal to 0, it means a power 9, b power 9. If m is equal to 1, so it means a power 9 plus 4, and so on. So F accepts the word, which is, you can see, a power 9, b a power 4, m, and b power 9. And b also have here yani 2 states. So here it is 2, and here it is n, where yani m and n can be 0, 1, 2, 3, and so on. M and n not being simultaneously equal to 0, which shows that F accept a word that are not belonging to the language. So that's why yani it's not a regular language. Thus, there is no finite automata which accept the language L, and that language is basically what? It is a power n, b power n. Okay, so which shows that by the Kleene theorem that the language L cannot be expressed by any regular expression. It means that it is not a regular language. It may be noted that apparently, a power n, b power n seems to be a regular expression because people are confused usually that a power n, b power n is same as a steric, b steric, but in reality, they are basically not the same. But in fact, it is not. The observation made from this example generalize a theorem. If you can see here, what we are doing is we are actually, repeating this circuit. So we are doing what we call it as pumping. Pumping means repeating. Okay, so that's why the observation made from this example generalize a theorem which is known as a pumping lemma theorem, which is basically used in order to find out either the language is regular or not. Regarding the infinite regular languages as follows. Now let's talk about the pumping lemma. We have the initial version of pumping lemma. We call it as theorem number 13. We call it the pumping lemma version 1. We have another version of pumping lemma. We call it as theorem 14. Inshallah, Bismillah, we'll also discuss the theorem 14 as well. Now, Let's assume you have L as any regular language that has infinite many words. It's a regular language, but an infinite, because here we are talking for the finite, it is easy. But however, for the infinite, it is not that much easy. And we will take an example of the infinite languages. So let L be a regular language and the nature of the language is infinite. Then there exists some, for example, we divide that words into three strings, substrings, which is represented by X, Y, and Z. Make sure that Y cannot be null. It is impossible. Such that all of the strings of the form X, Y power N, and Z, where N is equal to 1, 2, and 3. And these are the words from the language L. Since L is R, we will assume that L is a regular language. So for sure, there will be a finite automata that accepts exactly the word L, the one that we will select in order to apply a pumping lemma. Let W be some words in L, okay, that has more letter than the states, because you know what we need? We need to make a circuit. So in order to make a circuit, we will make sure that the size, the number, the size of the strings must be more than the number of states in the finite automata. Why? Because we want to define the part which is a circuit which we will be using in pumping. When we generate a path through a machine, the path cannot, because here you can see, for example, as we said, that the words or the length is more than the number of states. So if I have a word which consists of 13 length, and I have finite automata which consists of 5 states, so it means that for each of the character in this word, it is not necessary that it will visit a new state. It might visit the same state again. Okay, so that's why you can see here it is written, when W generate a path through the machine, the path cannot visit a new state for each letter or character it reads, because there are more letters than the state. This is an important point, because there are more letters than the state. It means there must be some sort of circuit or might be a loop. Therefore, the path must at some point revisit the state that has already been visited. It means that the path contains a circuit. Now let's see how we can apply, or how we can, what is basically inside the pumping lemma. We have a word W, okay? We divide the word W into three parts. One is X, another one is Y, another one is Z, okay? Now let's see. Starting at the beginning, let X denote all the words of W that lead up to the first state that is revisited. When you make a finite automata, see, for example, the finite automata is available. So what we will do, we will take X as all, those letters from the W, okay, that lead up to the first state that is revisited. Yani you started from the first state, and then you again come back to the first state. When you come back to the first state, so all the letters in between will belong to the X. Note that X may be null. Okay, for example, if you came to the first and you still be in the first and there is no intermediate state, so in that case it is possible you can make even X null, you can even make Z null, but you are not allowed to make Y null. Now, part two, starting at the letter after the substring X, we have another letter which is Y. It denotes the substring W from W, okay, that travel around the circuit, coming back to the same state that the circuit began. Because there must be a circuit. Keep in mind, as I told you, that when we are taking the number of letters more than the number of states, so for sure there must be a circuit. And that circuit always belongs to Y, and come back to the same state that circuit began, because there must be a circuit, so Y cannot be null. This is a very important point, that it is not possible in case of pumping lemma that Y will be null. And Y contain the letter W for exactly one loop around this particular circuit. Now let Z be the rest of W, starting at the letter after Y and going to the end of the string of W. Note that Z could be null because it is must that it must contain one circuit. It might be possible that it contain two or three circuits, but one circuit is must, and the circuit that is must is basically belong to Y. Or the path or the path for the Z could be also loop around the Y circuit or any other. That means that Z does is arbitrary. Clearly from the definition of these, we have for sure what we need to do is we need to make W is equal to XYZ, and we need to make sure that this particular word must be accepted by that particular language. Recall that W is basically accepted by the finite automata if the language is a regular language. For example, consider this example. Here what you have XYZ. Okay, this is the X part, this is the Z part. Okay, in this case X does not contain any circuit, does not contain any circuit, which is absolutely fine. But as you know that Y must contain circuit, so here it is repeated one time. Okay, then it is X, Y, and Z. If it is X, Y, Y, Z, so Y will be repeated one time and then it will be repeated two times. All the language L must be of the form W is equal to X, Y power N and Z for this to be accepted. If there were not in this form, it means then the finite automata will not have such a trace, and we know yani we need this trace in order to find out a part which we need to pump. And that's why what we need in this case, that the number of states must be less than the number of words in string, the string that we have selected. Now, what is the path for the input string, which is X, Y, Y, Z? Here we have seen it will be X one time Y and then again time Y and so on. So the path follows for the W. In this case, what we did, this particular circuit will be repeated two times. So these are the things which is written based on the path, and we have already discussed the path. So that's why, hence the string X, Y, Y, Z is basically accepted by the machine. So it means, therefore, it must be in the language. Now, if it is three times, so the circuit will be repeated three times. If it is four times, and so on. So that's why N either equal to 1, either equal to 2, 3, and so on. So it is called, we call this process as pumping because we pump some more stuff into the middle of the word and swelling it up without changing because we are not changing anything in X, anything in Z, we are just pumping Y. So it is called lemma because although it is a theorem, its main importance is as a tool in proving the other results of more direct interest in order to find out either the length is regular or not regular. Keep in mind that in pumping lemma, it does not give you always, it does not work in all the cases. Okay. So it is a theorem, but it is not applicable in all cases, while in case of the word, usually theorem is applied in all the cases it is true. However, in the case of pumping lemma, sometimes it is possible that, it gives you wrong results as well, the initial version. That's why we move to the other version of pumping lemma. Now, let's consider an example. Consider we have a finite automata that consisting of 95 states, okay? And here the word is A power 96, B power 96. A power 96, B power 96 means how many number of strings we have. It is basically 96 plus 96. So for sure, Yani, it is the string size is greater than the number of states. Why? Because we need to have a circuit. The first 96 letters of this input string are all basically what are all is, and trace a path through this machine. If we need to trace the path, always cannot visit a new state. Why new state? Because the number of states is less than the character with each input letter read, because there are only 95 states. Therefore, at some point of the path, it returned to the state from where it has started or already visited. Even if only one returns once, we can say that the path contains the circuit. A circuit is a loop that can be made up of several edges. This is a very important thing. There's a difference between a loop and there's a difference between a circuit. Okay, now consider this example that consider the following finite automata having an infinite, this is an infinite language because there's a loop and even the circuit as well. and has only 6 states. Here you can see we only have how many states? We only have 6 states. And here we have a string which is w is equal to 1, 2, 3 times b, then a, b, a, and then b, a. So you can see here what we did. We have, from you, if you can come here, okay. So look, you can see we have b, a, a, A as one this circuit. We also have another circuit which is B, B, A. Okay. So if I need to divide this one, so you can see I can take Y as that part which is, which contain a circuit. So here B will be X, Y will be the part which consists of the circuit, because I don't have any part which says that B, A, A, because here we have B, A, and then B. So this is the only one that contains the circuit. So this will be Y, this will be X, and after that the remaining will be Z. So after looking at diagram, I have decided what will be my Y. What happened to the input string? Okay, if, because this is XYZ, if I need to make it as X, Y, Y, and Z. Okay, so it will be X is equal to B, one Y is B, B, A, another Y will be B, B, A, and the Z will be B, A, B, A. Okay, so that's why it says that this string will be just looped twice around the circuit and it will be accepted. Even in the case of 3 or 4 and so many number of times, what will happen? It will be accepted. Keep this thing in your mind, girls. And when we need to decide why, how we can decide, we will look at the diagrams and then we will see whatever. If we have multiple circuits, then we have a freedom. You can decide any one of them. But if there is only one circuit, we can take the value of Y in such a way that it belongs to the circuit. So inside, the question, the string will be given, okay? And then you have to, and we will give you also the finite automata, and we will ask you to select X, Y, and Z, and then find out that either a language is regular or not using the pumping lemma. Now, suppose that A power n, B power n, okay, L is the language. The pumping lemma states that there must be a string as per the pumping lemma, that what we need to do is we need to divide it into X, Y, and Z, such that all the words of the form X power n, X, Y power n, and Z are in L. Is this possible? We will see. For example, here in case of pumping lemma, you need to divide it into 3. One is X, another is Y, another is Z. Okay, if Y is, for example, now the most important thing for us is basically this Y. Now, if Y is made entirely of A's, then we will pump it. Then the words, for example, because it is A power n, B power n, having equal number of A's and equal number of B's. And in case of Y, we have to loop it, we have to pump it. So if Y only A's, and if we will pump, then the number of A's will be more than the number of B's. If Y will be only B's, so, and when we pump, so the number of B's will be more than the number of A's. If Y is the combination of A's and B's, so for example, if we have 3 times A, 3 times B, and we take this one as Y, that Y is equal to AB, and then if we repeat, for example, Y 2 times, so it means AB, AB, and here 1, 2 times B, and here A 2 times. So in this case, this string does not belong to a language which is A power n, B power n. Why? Because if there is A, all the A's must be before B's, but you have even this A which is after the B. So this means that X, Y, Y, Z would have 2 copies of A, B. And this actually, this is something that is not allowed in our language, which is defined. So that's why it is not a regular language. So here let L is equal to A power n, B power n. We know that it is basically what? It is basically a non-regular language, and we have already defined this in the previous slide. We can show that the equal, for example, we know that A power n, B power n is a non-regular language. So, as per our previous discussion, that the because it's closed under intersection. So the intersection of two non-regular languages are basically, sorry, of the intersection of two non-regular are non-regular, and the intersection of two regular are the regular languages. So now here we will see about the, for example, equal. We can show that a language equal all the words with the same total number of A's and B's are also non-regular, because if it is non-regular, equal is representing the same thing. So look, the language A power n B power n is the intersection of all the words defined by this one and this one, because A power static, as I told you, that A star, B star is not a regular language, but there are some subsets of string which belong to the regular language. So what we did, we take A star, B star, and we take the equal, and when we take the intersection, for sure the intersection of these will be the regular. If equal were a regular language, then A power n, B power n would be the intersection of two regular language. This is based on our, previous clean, what we already discussed in the properties of a regular language and in the clean theorem. Additionally, it would need to be regular itself, which is basically it is not. Therefore, equal cannot be a regular, because as what I told you, that as per the clean theorem, okay, the intersection of two regular languages are regular. Okay, here yani we know that equal cannot be a regular, because we know that A power n, B power n is a non-regular language. So since even A power n, B power n is not a regular language. Now, this is the first part. Let's talk about, theorem number 14. Theorem number 14 is the version 2 of the pumping lemma. Let L be an infinite language that is accepted by a finite automata consisting of n states. Then for all the words in W, which is defined in the language L, will have, like, because we need to pump something, okay, will have more than n letters, because we want the length of the string should be more than the number of states. There are the strings which consist of X, Y, and Z, where Y is not null, and where the length of this thing is very important, where the length of X plus the length of Y does not exceed n, such that this is something that is mandatory in case of the pumping lemma part 2, which is theorem number 14. So W is equal to X, Y, Z, all the strings of the form X, Y power n, Z, where n is equal to 1, 2, 3 are all in n. So let's consider this particular example, which is considered a language which is A power n, B, and then A power n. There will be one time B, and here you will be having n occurrences of A in the start as well as n occurrences of B at the end. We shall show that a language palindrome is a non-regular language. We cannot use the first version of pumping lemma to do this, which is X equal to, for example, A, Y will be equal to B, Z is equal to A. Satisfying the lemma, but do not contradict the language. All the words here, they are in palindrome. If this language were regular, then we know that the pumping lemma should hold true. But here, it is not possible. Okay. So X, Y, Z and X, Y, Y, Z both need to be in L. Now consider the language which is A power n, B, and A power n, where you have this as a string. Okay, however, let us consider one of the finite automata that might accept this language. Let's say that the machine we have consisting of, this is our assumed word. It is not necessary you will take 80, you will take anything. But as you know, that the restriction is that the number of the states must be less than the length of the string. And we have A power 80, B, and A power 80. Now the palindrome is, so must be accepted by this machine having more letter than the machine states. So we break W into X, Y, and Z. I cannot take all A's as X, Y, because as per the rule of theorem number 14, it says that the number of, for example, the number or the length of X plus Y, here you can see it is written does not exceed n, and here A is 80. So that's why what I need to do is I need to divide it in such a way that means that we can form XYZ. We are adding yani more A's. So here, what I will do, I will take a part of yani A. I cannot even take the whole A. I will take a part of A's as X and also yani some part in Y, and the remaining will be a part of yani Z. So you can see here that means that we form a word X, Y, Y, Z. We are adding more A's on the front of W, but we are not adding any A's at the back. Okay. Why? Because we are here yani taking a part of yani A's in X and the remaining part in BAY, because we cannot exceed yani 77. So that's why you can see here more than 80, then you have B and then A 80. So in this case, you can see this indicate that the palindrome is not a regular language, because this will not be true. Let's consider another example where it says that consider a language prime where A power P, okay, P is a prime number. And you can see P can be either repeated 2 times, 2 is a prime number, 3 times, 5 times, and so on. Is prime a regular language? If it is, then it means for sure there must be a finite automata, or there must be a regular expression that accept exactly these words. Let us keep one such automata in mind. For example, let us suppose just that we have a finite automata that consists of 345 yani states. Okay, let's choose a prime number, that is because the number of states should be less than the length of the string. So what we did, we need to consider a number which is greater than 345. So let's, sorry, 345, yeah. So what we did, we have, so the length of the string will be 347. And keep this thing in your mind that you have all yani combination of A's. Then A347 can be broken into X, Y, and Z, such that X, Y power N, and Z is also the prime for any value of N. And you know that X, Y, and Z are just, the combination of A's. For example, let's see if we will take N as 348. Keep in mind, girls, this N is not yani this one. Okay, this N does not means the occurrence of P. N here means that this power of Y, and indicate basically the power of Y. So N is equal to 348. By pumping lemma, what we will do, we will make X, Y power 348, and Z must be prime. So what we did, you can see X, Y power 348, and Z, as these are all A's, what I can do, I can write, because X will be also A, Y will be A, Z will be A. What I will do, I have written X, Y, Z, and here I wrote Y 347, because you know that Y power 1 and Y power 347 is equal to Y power 348. So that's why, we wrote this thing, and then X, Y, Z, and this particular Y, this one, we wrote it at the end. We can write this because X and Y are just, combination of A's. If it is a combination of A's and B, then we cannot write. It does not matter in what order we can concatenate them. All the matter is how many A's we can end up at the end. So, you know that A, okay, we have already yani discussed this thing, that what we did, we have when we talk about, we take an example of occurrence of A's as, for example, 347. Okay, so what we did, we have the occurrence of A's as, yani we have this XYZ, and here is Y power 347. So we replace the XYZ with A power 347 and this Y 347 as it is. This is because XYZ came originally from breaking up A 347 into 3 parts, because we have taken this example as 347. So what we did, into 3 parts. So we know that Y is something that is non-empty, strings of A. Let us, for example, if we will consider, okay, Y as A power M, but we will make sure that M is not allowed to be 0, because Y is not allowed to be empty. So what we did here, we wrote A power 347, Y power 347 from here. then a power 347 y m, because it can be pumped any number of time, and then 347. Okay, and we know it's all any, because y is also a. So what we did, we take it as a power 347 plus 347, we take a common a, and here it is m, and 347 m plus 1, we take 347 as common, we left with m plus 1. Since m is not equal to 0, so we know that 347 m plus 1 is not a prime number, but this is a contradiction, since all the strings in the prime number are of the form, what are of the form a power p, where the exponent is a prime number, but here an exponent may not be the prime number. This contradiction arose from the assumption that a prime is yani was a regular language. Yani we make an assumption that prime is a regular language, but prime is not a regular language. Therefore, we came to a conclusion that a prime is basically what? Prime is basically a non-regular language. So this is all about non-regular language. Thank you very much.